सभी ज्वाइन होने दो, फिर स्टार्ट करेंगे क्लास। जो लोग अभी ज्वाइन किए हैं वो अपना अटेंडेंस पोस्ट कर देंगे एलएमएस पोर्टल पे। लेट मी चेक फर्स्ट हाउ मेनी ऑफ यू गिवन द अटेंडेंस। नौ लोगों ने अटेंडेंस दिया अभी तक, so kindly put up your attendance।
एक्सक्यूज मी सर। सर
हाँ भाई।
सर मेरा अटेंडेंस बहुत सा हट गया है सर।
मतलब बहुत से
मतलब जो
कैसे
परसेंट ये कम हो गया था सर अपने से। चेक किया तो है।
कब कब बात कर रहा है?
ये सर देखे तो कम है, आज देखे तो 3 ही को दिखा रहा था और एब्सेंट दिखा रहा था अपने से।
एब्सेंट दिखा रहा है एक से। हम देख लेंगे भाई एक बार। ठीक है फिर तो इन्फॉर्म
ठीक है
करेंगे।
सर।
हाँ। वैसे तुम अगर डेट बता पाओ किस दिन एब्सेंट दिखा रहा था, हम को चेक कर लेंगे। ऐसा
25
क्या
में एब्सेंट
करना
दिखा रहा था सर।
25। 25 में तुम था प्रेजेंट?
यस सर।
25 का एब्सेंट दिखा रहा है, हाँ एकदम। क्योंकि जो अपने से अटेंडेंस बनाया उसके अलावा हम किसी को अटेंडेंस नहीं दिए। ठीक है, तुम नहीं बनाया होगा। ठीक है, जो भी है बन जाएगा। इसमें क्या है। So in the electrical machine we were discussing about some टॉर्क स्पीड कैरेक्टर मेनली क्या है कि जो लैब है टॉर्क स्पीड कैरेक्टरिस्टिक्स ऑफ डीसी मोटर है तो उसको समझने के लिए फर्स्ट यू हैव टू नो दिस इलेक्ट्रिकल मशीन चैप्टर दैट्स व्हाई आई एम टेलिंग दिस taught teaching this chapter that means unit 4 to understand the lab process. Okay, so we were discussing in the previous class about this torque. Okay, so the relationship or the graph between torque and slip is called your torque slip characteristic. So depending upon this notation, or you can say depending upon this equation, that is torque is directly proportional to the slip, and that slip is related with in another form, that is torque is directly proportional to slip. This is rotor resistance. This is the rotor resistance square plus slip induced with the slip induced with the reactance, rotor reactance, the squaring. Okay, the main graph that we're discussing, that is torque slip characteristics, as in the starting point your rotor speed is equal to your synchronous speed, that is n equal to ns. Then in that case the slip was 0. As the load is increasing, the torque, or you can say from the starting point of view, as the load is increasing, the torque is increasing, because you are increasing the load from O to C, and C is the point for the full load. And after full load, if you further increase the load, then the torque will also increase, and this will achieve the maximum torque, and the maximum torque is related with your Tm, and on the slip side it is written as your Sm, or you can say maximum slip for the maximum torque. Okay, as you are increasing, but after point A, further if you increase the load, then torque will break down. Torque will break down and it will start decreasing from A to B, and it will start decreasing as the torque is decreasing, but as the speed is further decreasing, that is from the your rotor speed equal to synchronous speed, if you are decreasing the your rotor resistance, your rotor speed, that means you are going through n equal to 0, you are making the rotor speed as n equal to 0, and you are decreasing the value of rotor from synchronous speed, and you are decreasing from slip 0 to slip 1. So at this moment, when the slip is 1, then the rotor speed is 0. That means this is your standstill condition. This is called standstill condition. That means for further increasing load after point A, when you increase the load, then torque will decrease, but the slip will increase, and it will achieve the point B. At this point should not go to this x-axis, because if you decrease the further point, that means this is your starting point for your torque. That means beyond this value, or beyond this point, or you can say beyond this line, this torque cannot be decreased, because at the starting point this is your starting torque, and this starting torque is related with your some other formula, that is k involved. There is involvement of k, then s, then e2 square r2 divided by r2 square plus s x2 square, that we have discussed in this case. So in the starting point, the value of the slip will depend, that is the starting point, the slip value of the slip will be 1. As you can say, the value of the starting point at, okay, for the starting point, the value of the slip will be your n equal to it is taken as 0, but in standard still condition the starting point will be 1, and at the starting point, this when you put the value of s equal to 1, that means this equation will become e2 square r2 divided by r2 square plus x2 ka whole square, just like your impedance term in the denominator part, and the rotor resistance is multiplied with the square of the rotor emf. That will be the your starting range, starting torque. So that's why this at after point B, it will be not decrease, it will not decrease to point x, or you can say point to torque equal to 0. So for that case, it is written here oa is your stable region, oa is your stable region, but after point s equal to sm, the stable region will be unstable. That means after point this, after this straight line, there will be unstable region. That means this is dotted line is related with a unstable region, or you can say for the slope path, as you know, the slope is will be 0 to a, when you draw a slope, that will give you torque tm. Slope means tan theta. If you take a theta angle between this x-axis or slip axis with this load graph, that means tan theta will give you point, this point, that is SM20. Let us say this is named as your L. The LA divided by OL, that will give you the your slope of the line, and for that value the slope will be positive. But after this point, let us say after this point, when you draw a slope, it will be a negative. Yeah, if you draw, this is the point. Let us say this is the point where you have marked this point as the point of consideration. When you draw a slope after this point, that means if you increase further, in the backward side, it will include with the x-axis, it will cut out by the x-axis or slope axis. In that case, the theta will be negative, tan theta will be negative, or you can say the slope of the region will be negative. And for the negative slope, the region is called unstable region. So from this graph, torque slip characteristic, you can say for the stable region, this is the stable region as you are increasing the torque, and when you decrease the torque, that is your unstable region. That's why this dotted dark black line is named as stable region, and this is dotted line is named as unstable region. This is point A, that is your maximum torque. This is the full load torque, that is T equal to FL, and this is the starting torque. This is the starting torque. So this is all about the torque slip characteristics. We will discuss something else about this torque in elaboration part in some other topic we will discuss. So according to this graph, the explanatory part is given here. That means torque slip characteristics have three regions. First one is a stable operating region. This is your stable operating region. This is your stable operating region. This is your unstable operating region. That means this is unstable operating, and there is a normal operating region. And this is the stable region, or you can say this is the normal operating region up to this point. Okay, so there are three regions when the slip will vary accordingly. This what is the stable region. Now S is very small. Stable region means for this value, you can see S equal to 0 to S equal to 1. The value lies between 0 to 1. So we can say that the value between this S equal to 0 to S equal to 1, let us say this is your 0.3 or 0.4 will be there, as you, this is not the middle point between 0 to 1. So let us consider this 0 to SM varies from 0 value to 0.3. So the range of the slip that is for stable region is very much low, and this value SM will be denoted for your particular consideration. But that means if you take some numerical term, or you can say in practical case, the size of the machine will vary and the speed will vary as the SM will vary. That's why this is written as S is very small. Then if the S is small for the starting position or for the stable region, if S is very small, so you can see that the S x2 square, that is the denominator term, that is you can see from here, this S x2 term, this is the very small term, so it can be neglected. And if you neglect this term, that means it will become R2 divided by R2 square. That will make T is inversely proportional to 1 upon R2. That means from this equation, that is if in the starting portion, if the slip value is very small, if the slip is small, that means this can be ignored. S x2 whole square, this term can be ignored, and as the value of slip is small, so it can be neglected. So from here, there will be only term left, that is R2 divided by R2 square. When you cut out denominator, then that relation will become T is inversely proportional to R2. That is given here, that is hence x2 square is neglected. T is directly proportional to r2 square, that is T is directly proportional to s. As if the r2 is constant, then this torque will be directly proportional to s. But if the value of r2 will not be constant, that means that this torque will be relatable to your slip as well as your rotor resistance. So for this stable region, it is written as the load is increasing. As the load is increasing, you can see from 0 to A. First, you should increase the value 0 to C, that occurs the full load torque. And after beyond that, if you further increase the value of the speed, if you decrease the speed of the rotor and you are increasing the value of slip, that means this C will move to point A. That means this is the stable region. And for this stable region, it is written here, that is if you increase the load, the torque is increasing. You can see this is the torque is C to A, the torque is increasing, full load become maximum torque. And for this particular region from C to A, you can say corresponding to point C, when you draw a perpendicular on the slip axis, you will get somewhat somewhere in this point. And after point A, this is getting S equal to M, so the slip will be increasing from some 0.1 to SM value. Let us say SM value is 0.4, so this will be 0.1 to 0.4, so slip will also increase. As the load is increasing, the torque will increase and slip will also increase for your this stable region. But in this unstable region, you can see as your load is increasing, torque will decrease, but the slip will further increase. Okay, now you can see characteristic is approximately straight line. So from here you can see that T is directly proportional to S, and if the T is directly proportional to S, that means torque is directly proportional to slip. That means as you increase the slip, the torque will also increase. That means this is a type of your straight line function. A straight line equal to the equation that gives the straight line equal to y equal to mx plus c. C is your intercept drawn on the y-axis. Normally, if we have dealt that term for the straight connection in this x-axis and y-axis, in mathematical term, when you draw a straight line function, the equation of that straight line is given as y equal to mx plus c, and c is your intercept. Here you can see that intercept you can take as t starting torque. This is the starting torque, so intercept will be t starting torque. And if you draw the line in terms of y equal to mx, that means m is your slope, and when you draw, then slope is given as this one sm divided by os. This is your s, so a s divided by os, that will give you the value of m. So from there you can see that directly proportional give you the straight line function. This straight line torque and slip is a straight line equation, so it is given as the straight line equation for the your starting point to maximum torque. That is what given here, written here. Characteristic is approximately straight line. Now after this point, this is a slight curve. There is a slight curve. So at this maximum peak point, there is a curvature to draw. There is a curvature to draw in the denominator part. Wait a second. So we were discussing about this graph, torque slip characteristic. So for this region, the characteristics of there is a slight curve. That is, this is just looks like a straight line. That's why this is related with the torque and slip. That is directly proportional to, as you are increasing the slip, the torque is correspondingly increasing. That's why this is termed as your straight line. The next part is your unstable region. Unstable region is this one. This is your A to B. This is your unstable region. This is a unstable region. You can ignore this BC as this is your unstable region. So when S is, it is written when S increases, that is when slip increases further from SM. That was your point. This is your SM. When you further increase the slip, that means torque will decrease, but the load is further increased. That is what it is. When S increases further from Sm, the region is unstable. Okay, S is high. That means sleep will be higher as the sleep is increasing. Is increasing term. It is starting from 0, then it becomes Sm. Let us say this Sm is your 0.4. When you further move in the positive x-axis or sleep axis, then sleep is increasing. As the sleep is increasing, the torque is decreasing. As you can say, the torque is moving from point A to B, and that's why this is called unstable region. For that unstable region, S is high. Okay, fine. Then R2 square can be neglected as compared to S2 square. And for this unstable region, when you draw this graph, when you according to equation, for the unstable region, this R2 square will be neglected because the rotor resistance will be very small, and for that value, this if you decrease the value, the final value for the unstable region become this one, that is torque is inversely proportional to S upon S x2 square. When you solve this, you will get this one, 1 upon S cancel out one slip, that means S upon S x2 square. And for the value of x2 will be constant by the manufacturing process, this torque will be inversely proportional to S, that means inversely proportional to your slip. So for the unstable region, this will not be a straight line. This will not be a straight line. It will be a slightly a curve. Okay, as a slip is inversely proportional to the inversely proportional to your torque. Okay, so for this reason, as you increase the load, the slip will increase, but the torque will decrease. As the load will increase, the slip will increase, but the torque will decrease. And the characteristic is approximately rectangular hyperbola. Okay, this is your rectangular hyperbola. You can see this from A to B. You can see this. This is a rectangular hyperbola function. This is a straight line from O to A, but for A to B, this is a rectangular hyperbola. You can say that. Now, for that, when load further increases, N decreases, S will increase. Leads motor to standstill condition. That means when you increase, as you can say, this is your rotor speed is equal to synchronous speed, but the slip was 0. As the slip increases, the rotor speed is decreasing. As if first it was at synchronous speed, then as this is decreasing, the value become n equal to 0 for this maximum slip. That means this is your standstill condition. When the rotor is does not move further, that means this is called as standstill condition. That is what written here. When load further increases, n, that is speed, from synchronous speed it is becoming 0. That means n is decreasing, rotor speed is decreasing, S is increasing as Sm is becoming 1. That Sm value is 0.1. We have taken as assumption that Sm has 0.4 value, then that value is increasing from 0.4 to 1. And for the condition, leads motor to a standstill condition. As the n becomes 0, the motor will operate at standstill condition. Okay, that's why this motor cannot be operated at any point in this region. So that's why this operation for this region, the motor should not be operated for unstable. As you can see, this is unstable. As by the name itself, you can see that for the unstable region, the motor is unoperationable. The motor is unoperationable. Okay, and for the normal condition, this is the normal region A to D. This is the normal condition A to D. No, nothing is there. A to D. So the normal condition is given by this graph. Okay, this is the A to D in the stable region. Okay, now low slip region, the motor can be continuously operated in this region. Okay, that is the A to D. Now torques are three types of torques we have discussed. That is, first one is starting torque, second one is your maximum torque, or you can say pull out torque, third is your full load torque. And according to the graph, you can say first one was your starting torque, then it is your full load torque, then it is your maximum torque. First it was starting, then attains the full load, then it will achieve the maximum torque. That is what the first starting torque, then full load torque, then maximum or pull out torque. This maximum is also known as pull out torque. Now starting torque is given by the motor produces the torque when S equal to 1, the X is maximum, S is maximum. That means your N equal to Ns, rotor speed equal to synchronous speed. In that case, this is the starting torque. Then maximum torque is also termed as your pull out torque. Okay. Now full load torque, we don't have to discuss all these things. Losses. Okay. The next topic is your losses. We will discuss losses in some later point of view. So again, we can see that this torque slip characteristics of induction motor can be for the full load. This equation is given by this torque equation. That is torque equal to, we have removed the proportionality constant. So from here you can see that, this is the proportionality constant, this is the slip, this is the rotor, EMF, this is the rotor resistance, and accordingly the torque slip equation can be derived for full load torque. And for this value, if you draw, when k, where the value of k is 3 equal to 2 pi ns, this k having the value of 3 upon 2 pi ns. 3 upon 2 pi is constant, and ns is your synchronous speed in rps. So this is the synchronous speed, this is your synchronous speed ns. If you want to write ns equal to synchronous speed rpm, you can write it, but we have taken this as, it is written here, ns dash is your in rps, rotation per second. That's why it is divided by 60. So if you want to take in rpm, you can write it at rpm, that is ns in terms of 60 into ns, matlab 3 upon 120 pi ns, that will become 3 into 120 pi, or you can say, you can just put the value of ns dash here. Okay, that is ns upon 60. You will get 180 divided by 2 pi ns. Okay, that means 90 divided by pi ns. Okay, all these things are known. X2 is rotor reactance, it is your induced EMF in rotor at a standstill condition, E2 is your rotor resistance, S is slip. Okay, fine. So to draw this equation, or to draw this graph, as this graph that we have drawn, theoretically it is explained here, how we can draw this graph. These things that we have discussed is already given in this thing. So from here, from this graph also, you can see that in the stable region the value of slip is small. So this is your stable region, this is your stable region, and this was your unstable region. And for this unstable region, the slip is large, the value of slip is larger. And with the increment in slip, the torque will decrease, as this is the inversely, torque is inversely proportional to your slip. A rectangular hyperbola, it is look like your straight line. Okay, this is the maximum torque, you can see that. So these all things we have included. Now for this particular section, there is another concept regarding a rotor resistance. For this, when you draw torque and slip, and for the value of rotor resistance for the upper portion, for the stable region, if you write that is torque is in directly proportional to a slip, when you draw this torque as a starting point, and torque is directly proportional to, if you ignore in the starting region, s will have the small value, so it was ignored. K is constant, so you can ignore this. E2 is also constant value, so you can ignore. So from here you can read that T is inversely proportional to R2 for the starting portion. T will be inversely proportional to R2 if the R2 is not constant. I have already told you. So from here you can see that, from here, if the R2 is not constant, that means you can take R2 divided by R2 square, that will become will be inversely proportional to R2. That means as the value of R2 increases, torque will decrease. With the increment in rotor resistance, torque will decrease. That is what given here. You can see it is written here, effect of rotor resistance on torque slip characteristics. Okay, so it is, you can see that this is the red one, this is the blue. The different type of resistance are given by different colors. So from here you can see that, to see the effect of rotor resistance on torque slip characteristic of induction motor, consider a slip ring induction motor. We have to consider a slip ring induction motor. We have discussed two types of induction motor was there. First one was your wound rod induction motor, or you can say slip ring induction motor. Another one was your squirrel cage induction motor. So for the rotor resistance method, we have to include the slip ring induction motor, in which additional resistance in the rotor circuit can be introduced. As in the circuit diagram of slip ring induction motor, we have dealt this diagram. We have dealt with this your circuit diagram of your slip ring induction motor. There we have used a star connection in the stator winding. Then we had connected the slip ring with a rotor resistance, or you can say rheostat, that was connected. So in the starting point, so for it is written here, the rotor reactance is still condition x2 remains constant, that we have discussed. Now the maximum, as you can see from this graph, as the value of R23 is greater than R22 and R21, that means the least value is R21, as you can say, the least value will be R21. So for a low resistance value, the slip will be achieved much faster than the other slip, as the you can say this R23 is greater than R22 and is greater than R21. So from this graph, first if you draw a smaller resistance, the slip will be achieved faster. That means torque will be achieved faster than the previous one or the other resistance. That means as the resistance increases, the torque will decrease. That means for the particular maximum torque, if you vary the resistance, that means maximum lowest resistance will occur at the first point. Then as the time increases or the slope increases, as you can say, the slip will increase. Ns minus nr will increase with the increment in your resistance, with the increment in resistance. Okay, so at the starting point, the highest value of the rotor is taken as R2 equal to X2S, or you can say rotor resistance when become your rotor reactance. In that case, the slip will become 1. Okay, so that means torque is inversely proportional to your rotor resistance. Okay, you can find here. So this is the function. This is the explanation of rotor resistance in terms of your induction machine. This is not a topic of our study, but we have considered this one. Okay. Now further we will discuss this one. This one was your torque. So you can take the screenshot of this your torque slip characteristics from here. All of you must take the screenshot. That is torque slip characteristics. This graph normally. This is the important graph for your torque slip characteristics. Here you can say this is your braking region, this is your motoring region, this is generating region, or you can say this is your induction generator region. It is also termed as your induction generator region, or in this called induction motor region. Okay, there is two different, that's why it is named as your generating region, and it is named as your motoring region. So this is your starting torque that we have discussed in the your torque slip characteristic. Because of the somewhat value of in the intercept, that is forming an intercept form on the torque axis. Okay, as you can say, this is the speed 0 at the starting point. At the speed is 0, the slip will be maximum, so it is taken slip as maximum value. As the speed increases, that means when you reach the value of the slip ns, that means at synchronous speed the slip will become 0. In this position the slip will become 0. Further, if you increase the value, value of the synchronous speed, then the slip will become negative. And for the negative slip, the region will be generating region, or you can say for the negative slip, the induction machine will work as a induction generator. Okay, from this graph you can see that as the speed is increases, then the slip will become negative. And for the induction generator region, the slip will be negative. And for the further process, when you reach say the double of the synchronous speed, this graph will not never touch the your slip axis. Okay, so this is the mainly all this explanation has been done. So normally this explanation was left. So for this particular reason, we just write or just make a note that is for a slip negative, the region that is generated is called induction generator. Okay, a second. We don't have to study this torque slip cat. We don't have to study this torque slip characteristics of single phase induction motor. Just up to this point, we have to study. Just let me read this concept. That is for motoring mode. In this mode of operation, supply is given to the stator sides and the motor always rotates below the synchronous speed. That means when you write the motoring region, or you can say induction motor region, then this can be helpful for you to make a note. Okay, that means in this mode of operation, supply is given to the stator side. That means you are giving the supply to the primary side, and the motor always rotates below the synchronous speed. As you can say, for this induction motor, this synchronous speed will not be achieved for the induction motor, because if you achieve the synchronous speed, or if you make the rotor speed equal to synchronous speed, then what will happen, that we have discussed already in the previous classes. For that motoring region, the induction motor torque varies from 0 to full load torque as the slip varies. Okay, fine, that discussed. The slip varies from 0 to 1, that is minimum slip to maximum value, that is for the maximum value slip to minimum value. Okay, fine. The slip varies from 0. Okay, fine, it is 0 at no load. That means at the no load, the rotor is rotating at synchronous speed. Rotor is at the rotor is at standstill still condition. That means rotor speed is 0. In that case, the starting slip was 1. That is written here. It is 0 at no load and 1 at standstill. From the curve, it is seen that torque is directly proportional to the slip. As you can say, this is your straight line. This is a type of a straight line. For the straight line, this torque is directly, you can say that this is your slip axis. So for the straight line, you can say that this torque is directly proportional to the slip. But for this region, that is for the your unstable region, this torque will be inversely proportional to slip, and that's why this is called as rectangular hyperbola. Okay, for the slip, that is more is the slip, the more will be torque produced, and vice versa. The linear relationship supply. Okay, fine. That was our induction motor motoring mode, or you can say torque slip characteristic. In the second form, it is for the generating mode. That is for the slip value is less than 0. Then what is written in this mode, the operation induction motor runs above the synchronous speed. So up to this point, this was your synchronous speed. But if you increase the synchronous, further increase the speed of the rotor beyond the synchronous speed, then induction machine will work as an induction generator. And for that particular reason, the slip will become negative. And you can say for the slip negative value, if the induction machine works, then it is called a induction generator. That is what given here. The stator one is connected to three-phase supply in which it supplies electrical energy. Fine. Actually, in this case, the torque and slip both are negative. Okay. Here you can say the torque is also negative and the slip is also negative. Okay. Okay, fine. That is not the main case for the induction generator. So the torque slip characteristics, if you have any problem regarding this torque slip characteristic, you can ask. Okay. So all of you must take the screenshot of this diagram, torque slip characteristics, and this one, motoring mode, the explanatory part. We will proceed further. Let me see. So significance of torque slip characteristic is completed. We will discuss now loss components and efficiency of the induction machine. Loss components and efficiency of the induction machine. Okay. I think you don't have any problem regarding your torque slip characteristics. That means you can just see this diagram and you can take the screenshot of this one. Wait. You can take this as a screenshot, or you can say you can take the screenshot of this diagram, this one, and from here you can explain it easily. Okay. And there is another diagram that you should take, this one, the torque slip with the variation of resistance. Okay. With the variation of resistance, you can take the screenshot of this diagram and you can explain as the torque is increasing, the resistance will vary. Okay. Mainly slip will vary with the resistance. For the smaller slip, the value will be inversely. As for the maximum value, the rotor resistance does not depend upon the maximum torque. As you can say, for different value of rotor resistance, the maximum torque is still constant. Okay, there is no variation in maximum torque for the different value of rotor resistance.